Okay, so I recorded this live and it didn't really work out too well. So I'm just going to kind of leave the slides up here and re-record the voice to kind of walk you through everything. So we'll use purple here. This is 11.8 binomial expansion with some probability in there. Now, this is the general formula you need to know. The probability of any of X event happening is the number of total combinations that could happen times the probability of outcome 1 to the x power, and really this is supposed to be the probability of n minus x. Sorry, I had that written down wrong. So let me n minus x. And so here's what all this means. N is the number of trials, x is like the desired number, P is the probability of outcome 1, and Q is the probability of outcome 2. Now, there are some key things that have to happen in order for this to work. You can only have 2 possible outcomes. So things such as like win or lose, or right or wrong, or boy or girl, heads or tails, success or failure, those types of events. Now, that doesn't mean that the probability has to be 50-50. You know, if it's like a boy-girl example, yeah, that's true. You have a 50% chance of your child being a boy or a girl. But, you know, like getting questions right on a test, there are really only 2 outcomes to a question. You either get the question right or you get the question wrong. But you could have a 25% chance of getting it right. Say there's 4 questions and 1 right, or 4 choices and 1 right answer, and a 75% chance of getting it wrong. So different probability, but still only 2 outcomes. The next is that the outcomes have to be independent of each other. One can't affect the other. And lastly, and probably most importantly, the probability has to remain constant throughout. And so if the probability of a right answer is 25% initially, it needs to remain 25% throughout the entire problem for this to work. And so let's just kind of move on and see what kind of problems we're dealing with here. And so the first type of problem is they're just going to give you a number of trials, a desired number, and the probability of outcome P. Now, they might not give you the probability of outcome Q. In this case, they didn't. They only gave us N, X, and P. Well, if there's only 2 outcomes, and 100% of the time something has to happen, if the outcome of P is 30%, that means the outcome of Q has to be 100% minus 30%, which is 70%. And so now we're just going to plug this in where it needs to be. The probability of 4 occurrences happening, so the probability that P happens 4 times, you just plug it into here. 8, combination 4, and the reason that we use a combination here is that the order doesn't matter. If it were a permutation, if the order mattered, we would use P, but for these cases we won't. And so 8C4 times the probability of outcome P, which is 30%, to the 4th power, times the probability of outcome Q, which is 70%, to the 8 minus 4 power. Again, N minus X power. So 8C4 is 70, and 0.3 to the 4th power is 0.0081, and 0.7 to the 4th power is 0.2401. When I multiply those all together, I get 0.136, which is approximately 13.6%. So what that is saying is, through 8 trials, the probability of outcome P happening 4 times is 13.6%. So that's one type of problem you may have. The next type of problem might be a true binomial expansion problem. Now, try not to look at this all at once. Again, remember, I did record this live and it messed up, so now I'm just kind of backtracking. And so we started with this, x plus 2y to the 3rd power. And we want to expand that and ignore the probability of x and y for a minute. That's for later, just to kind of show. For now, just focus on this right here. I could do x plus 2y 3 times. X plus 2y times x plus 2y times x plus 2y, and I would get an answer. And that's cool, but that's not what we're going to use this for. We want to eventually use this to do probability. And so what we're going to do is we are going to set this up as, just like we did on the previous page, as a number of trials, a desired number, and we're going to set it up as this combination times p to the fourth power times q to the x minus fourth power. Some derivation of that. And so the first instance, we have 3, which is the number of occurrences right there, combination, and we're going to start with 0. You always start with 3c0. And then we're going to do x to the third power. Well, if we raise x to the third power, that means 2y has to be taken to the 0 power. Remember, these two powers here always have to equal whatever that is. And so next in line would be 3c1, because 3c0, the next logical step is 3c1, times x squared times 2y to the first. Then we do 3c2 times x to the first, 2y squared. And then finally we have down here plus 3c3 x to the 0, 2y cubed. And now we just need to simplify this, which is what I did down here. 3c to the 0 is 1. And then x cubed is x cubed, and anything to the 0 power is 1. So that's how I got that right there. 3c to the 1, so 3 combination 1, that's 3. And then I have x squared, and then I have 2y to the first power, so 2y. And then I move on to 3c2 is 3, and then x to the first power is x, and 2y squared is 2 squared is 4, and y squared is y squared. And then lastly we have 3c to the 3, which is 1, and x to the 0 is 1, and 2 cubed is 8, y cubed is 3. So now we need to simplify this. And the simplification, I'm going to kind of erase these red arrows here. The simplification is 1 times x cubed times 1 is x cubed. 3 times x squared times 2y is 6x squared y. 3 times x times 4y squared is 12xy squared. And 1 times 8y cubed is just 8y cubed. This is the answer. Right here. That's the answer. That's all we had to do. That was the answer. This is what they wanted us to do. They wanted us to expand this binomial. Now, where the probability comes in is, let's say that x had a probability of 0.3 and y had a probability of 0.7. Let's say I wanted to know the possibility or the probability of having 2 x's. Well, here's the situation where I have 2 x's. So I would take 6 times 0.3 squared times 0.7. And when I do that, 0.3 squared times 0.7 times 6 gives me a probability of about 37.8%. So there's a 37.8% chance that I'll have a result that has exactly 2 x's in it, given these probabilities up here. And so that's how we'll use it. And the last example I do will better show that. But before I get to that example, remembering to do all of these combinations here is a bit tedious. I want you to look at these numbers here that are supposed to be circled in red. And tell me the interesting thing that happens or that you notice. Think back to the last time we did binomial expansion. 1, 3, 3, 1. That should look mighty familiar. Yeah, it's the Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And so when I had x plus 2y to the third power, I'm going to look at the third row, the third power row on Pascal's triangle. Remember, you start with 0, so 0, 1, 2, 3. This row, would you look at those coefficients? 1, 3, 3, 1. So you can go ahead and do all of this combination nonsense if you want, but it's probably easier just to remember Pascal's triangle. So the final example that I do is going to be done using Pascal's triangle. So let's say that there are 5 questions on a test. 5 questions. And each question has 4 answer choices, meaning that there's a right response and a wrong response. Those are the 2 outcomes. There's a 25% chance of getting it right, 1 out of 4, and a 75% chance of getting it wrong, 3 out of 4. Well, I'm going to expand that. Wrong plus right to the 5th power. Well, if I look at Pascal's triangle, the 5th power row is right here. 1, 5, 10, 10, 5, 1. So I just put those coefficients in there. 1, 5, 10, 10, 5, 1. And now I'm going to put my rights and wrongs in there. So right to the 5th, 4th, 3rd, 2nd, 1st, 0. And now remember, their two exponents always have to add up to be 5 in this case. So w to the 0, 1, 2, 3, 4, and 5. And so now, how am I going to use this? Well, I've got all these blue and green circles here, so let me kind of show you what was going on. What I wanted to know with this green is, what was the probability of getting at least 3 answers right? Well, look, there's 3 answers right, there's 3 answers right, at least 3, and there's at least 3 answers right. So I'm going to plug these probabilities in for right and wrong, and then simplify. 1 times 0.25 to the 5th times 1 gives me 9.78 e to the negative 4. 5 times 0.25 to the 4th times 0.75 to the 1st gives me 0.015. And then 10 times 0.25 cubed times 0.75 squared gives me 0.088. And so when I add them all together, I get 0.104, which is 10.4%. So there's a 10.4% chance that on this 5-question test, I'll get at least 3 of them right. So that's a pretty small chance. Considering that 3 out of 5 is only 60%, I only have a 10% chance of getting a 60% on this test. Pretty crazy, right? And so you can use this to do all kinds of combinations. What if I wanted to know what's the probability of getting exactly 3 right and 2 wrong? Well, I would just look at this guy right here. What's the probability of getting exactly 5 wrong? Well, I would look at this one right here. Well, what about the probability of getting at least 1 right? Well, I would look at all of these, because all of those would tell me the probability of getting at least 1 right. And so you can use this to do a lot of pretty cool things. That is all. Please let me know if you have any questions. Goodbye.